In the realm of machine learning, our journey begins with understanding the intricate machine learning workflow. How do we navigate this complex landscape to craft truly effective projects? It all starts with clear goals and meticulous planning. From data collection to model training and evaluation, every step is crucial. Embrace the power of active engagement and vivid problem solving. Let's delve into the essence of machine learning, where insights and patterns transform into actionable intelligence. Join us as we unravel the mysteries of this dynamic process, step by step, from inception to implementation. In today's session, we dive into the essential components of a successful machine learning project. First, we'll tackle problem framing, ensuring a clear understanding of the problem at hand and its significance. Next, we explore data splitting, mastering the art of dividing data for optimal training and testing. Then, we delve into evaluation metrics, guiding you on selecting the right measures for assessing your model's success. Be wary of data leakage, as we uncover common mistakes that can compromise your results. And remember, starting with baselines paves the way for robust, sophisticated models. By the end, you'll grasp the intricate puzzle of an ML project, each piece harmonizing to craft dependable and impactful models. In the world of machine learning, success hinges on a well-executed plan, a structured path known as the ML lifecycle. Each stage, from data collection to problem framing, model training, and evaluation, is interconnected, forming a foundation for effective model building. But why is understanding this process so crucial? Because it's the key to avoiding missteps and creating models that deliver real-world results. Picture a puzzle where each piece must fit perfectly for the full picture to emerge. So, let's dive in and uncover the secrets to mastering the complete ML lifecycle. In the early stages of a machine learning project, the crucial first step is problem framing. This process involves clearly defining what your model should predict or achieve, translating real-world questions into specific ML tasks. Good problem framing is the linchpin of success, guiding data collection, algorithm selection, success metrics, and project scope. It ensures stakeholders grasp the project's essence and prevents wasted efforts on ineffective solutions. Remember, no matter how advanced your model, without solid problem framing, success remains out of reach. In the realm of problem framing, clarity reigns supreme. Avoid the pitfalls of vague objectives like making our email system smarter, which lack clear targets and evaluative measures. Instead, strive for precision. For instance, aim to predict email spam with measurable accuracy. Similarly, steer clear of ambiguous goals such as predict housing trends, and opt for specific tasks like forecasting house sale prices based on key features. By defining clear objectives, like these, you set the stage for success through measurable outcomes and well-defined parameters. In the realm of spam detection, we encounter a common real-world challenge, an overflow of unwanted emails besieging users. To address this, we frame the problem as a binary classification task, predicting whether an email is spam or not spam. The inputs for this task include email text, sender information, subject line, and metadata, with the output being a spam probability or binary label. Our primary goal is to minimize false positives, ensuring that legitimate emails are not mistakenly marked as spam while effectively capturing most spam emails. By refining this issue into a clear prediction task with distinct inputs, outputs, and success criteria, we make the project both manageable and measurable. In the realm of machine learning, Chapter 2 unveils the golden rule, the train/test split. Here lies the core principle: never judge your model using the same data it was trained on. This fundamental rule underscores the essence of machine learning, proving adaptability to new, unseen data rather than mere memorization of past examples. Data separation is paramount, as it unveils whether your model has truly learned patterns or merely regurgitated training data. Testing on training data breeds false confidence, leading to models that falter in real-world applications. It's akin to students peeking at exam questions before the actual test. Remember, the key to success lies in embracing the unknown. Ever wondered how the train/test split method really works in machine learning? In this process, we divide our dataset into two crucial sets, the training set and the test set. The training set, consisting of 80% of the data, is used to teach the model patterns and relationships. Meanwhile, the test set, representing the remaining 20%, is completely held back to evaluate the final model performance. Remember, the key rule here is that the test set should never influence training decisions. This separation allows the model to learn from 80 examples and then be assessed on 20 unseen examples. While common splits are usually 80/20ths or 70/30ths, the exact ratio depends on your dataset size. Larger datasets can opt for smaller test percentages while ensuring reliable evaluation. So, by carefully partitioning our data, we can ensure a robust and unbiased evaluation of our model's performance. What happens without proper splitting in your model? Overfitting. Instead of learning general patterns, it memorizes training examples, acing them but flops with new data. Picture a spam detector fixated on specific spam emails, missing new variations. And there's false confidence, your model seems accurate but only regurgitates memorized answers. The result? Disastrous performance, disgruntled users, and wasted resources. Moreover, invalid results, your accuracy metrics are misleading, offering no insights into real-world performance. Consequently, you're left clueless about deploying your model effectively or its business impact. An abyss of consequences awaits without proper model splitting. Remember, precision in training doesn't always translate to success in the real world. Once your model is trained, the next step is evaluating its performance. Not all metrics are equal, the right one depends on your specific problem and user needs. Choosing the wrong metric can lead to optimizing for the wrong aspects, resulting in a model that looks good on paper but fails in practice. Let's delve into common metrics and when to apply them effectively. Ever wondered how data scientists measure the accuracy of their predictions? Let's dive into the world of common evaluation metrics. Accuracy, precision, recall, and mean absolute error each offer unique insights into the performance of our models. Accuracy tells us the percentage of correct predictions, but beware its limitations with imbalanced data. Precision focuses on the proportion of true positives among all positive predictions, ideal for scenarios where false positives have high costs. Recall, on the other hand, sheds light on how many actual positives our model managed to capture, crucial in situations where missing a positive result is costly. Lastly, mean absolute error helps us understand the average size of prediction errors in regression problems, making it invaluable for tasks like predicting house prices accurately. These metrics serve as our navigational compass in the vast sea of data analysis, guiding us towards more effective decision-making. In the realm of choosing the right metric, consider the examples laid out before us. When it comes to spam detection, the key lies in precision, minimizing false positives to avoid irking users with blocked legitimate emails. Yes, some spam may slip through, but that's a lesser evil than missing important messages. On the flip side, in cancer screening, the focus shifts to recall, ensuring no potential cases slip by. This may result in more false alarms, but the cost of missing a cancer diagnosis far outweighs the inconvenience of extra tests. Remember, the choice of metric hinges on the costlier error, false positives or false negatives. So, what's your priority, precision or recall? In the world of machine learning, Chapter 4 unveils a silent threat, data leakage. This deceptive phenomenon sneaks in information from beyond the training dataset, granting the model an unfair edge that vanishes in real-world scenarios. Beware, as data leakage masks itself behind flawless testing but sabotages deployment. Let's delve into recognition and prevention. Picture a model excelling in testing, only to stumble in the real world, a cautionary tale of the dangers lurking within machine learning. Remember, data leakage can be the silent killer of your model's success. Data leakage in machine learning can be a silent saboteur, sneaking in through various entry points. Consider temporal leakage, where future insights warp our understanding of the past, like peeking at tomorrow's stock prices to inform today's trades. To combat this, restrict training data to only what was known at prediction time. Then, there's target leakage, where features spill the beans on the outcome, such as predicting customer churn using already cancelled subscriptions. Stick to using pre-outcome data to keep predictions honest. Lastly, train/test contamination muddles the waters by mixing pre-processing before the split, leading to skewed results. Remember, split first, then prep each set separately for clean, reliable models. Guard against these leaks to ensure your data insights stand strong. Takeaway: prevent data leakage by ensuring training data is pure and untainted, leading to more accurate and trustworthy predictions. Leaked data can lead to perfect accuracy in testing but a complete failure in production. Consider the house price example. Features like final sale price are only known after the sale, making them useless for prediction. On the contrary, clean data, with features like square footage and neighborhood known before listing, offer honest performance estimates and reliable predictions. Always ask, would I have this information at the time of prediction? If not, it's leakage. Predict wisely, based on what you know upfront. Why start simple? Before diving into the complexity of neural networks or ensemble models, always begin with a basic baseline. This straightforward model or rule serves as a reference point for comparison. Baselines reveal if your problem is genuinely challenging, if your data is valuable, and if intricate models are truly needed. Surprisingly, a simple approach often performs admirably, saving time and computational resources. If your sophisticated model can't outperform a basic baseline, something is amiss, be it your data quality, methodology, or problem formulation. Remember, simplicity can often be the key to success in model building. Ever wondered how to set a benchmark for your model's performance? Let's explore the world of baselines. Start with the random baseline. Making blind guesses gives you 50% accuracy in binary classification. But wait, here's the catch: the majority class baseline, predicting the most common class, can be surprisingly tough to surpass. Then there's the simple average baseline, predicting the mean of training data for regression tasks. And don't forget the simple rule-based model, where a touch of domain knowledge can go a long way. Remember, these baselines set the stage for your model to shine. So, which baseline will you choose to leapfrog these starting points toward excellence? Ever thought predicting not spam for every email could actually achieve 85% accuracy? In this email spam detection example, a simple logistic regression model already hits 94% accuracy, outperforming a complex neural network by just 10 percentage points. Sometimes, the simpler solution is not only good enough but also easier to deploy and maintain. Remember, accuracy isn't the only factor to consider in model selection. Just because it's complex doesn't mean it's necessarily better. In the world of data analysis, success hinges on clear frameworks and strategic decisions. Define your problem with precision, outlining key inputs, outputs, and success benchmarks from the get-go. Remember, data must be split, not mixed, to uphold the integrity of your testing process. Be deliberate in selecting metrics, tailoring your focus to the unique demands of each problem at hand. Beware of data leakage, ensuring predictive features align with real-world availability. And always start with simple baselines, grounding your analysis in solid foundations before diving into complexity. By following these principles, you pave the way for robust, insightful data modeling that drives meaningful outcomes. Let's put your knowledge to the test with these 5 quiz questions. Why split data into training and test sets? Answer: to evaluate if the model works on new, unseen data. Identify data leakage in a house price prediction model. Answer: using final sale price from the listing as a feature. When prioritize recall over precision? Answer: disease screening where missing a case is dangerous. Define a baseline model. Answer: a simple model or rule that provides a reference point. What is good problem framing for an ML project? Answer: predict if a user will cancel their subscription in the next 30 days. Well done! Remember, thoughtful data handling and problem framing are key in machine learning projects.